Video on maximum flow and what I sometimes kind of call informally backwards cuts. So I guess the key thing to remember for this video is that when we're trying to find the maximum flow of through a network, we're looking to make a cut that has the smallest possible capacity. So we always remember that the minimum cut equals the maximum flow. So just to kind of give you an example to consider, let's imagine we've got this network here and I've got the source, this node here labeled S, and this node labeled F at the end is like the sink, or you could think of it as start to finish. And basically with our directed graph, we've got sort of edges, and I've actually colored them in blue. And what I'm going to get you to think about or imagine is that this is representing, say, water flowing through pipes, right? And so each edge in the network has got water flowing through it because we're thinking of it as a pipe. And you can see all the weightings on it as well. So when we think about trying to find the maximum flow through this network from start to finish, well, obviously we need to remember that there's different ways that we can make cuts, right? So for example, if I start up here and cut off this edge of 8, what I want you to picture is that like that there cuts off the flow of water from A to E, right? So I've kind of tried to redraw that. So that's showing that we've cut off some flow there. So we're going to count that 8 when we are measuring the capacity of that cut. And if we continue the cut down, towards this edge of 7, well, then that gives us a cut that has, so again, we've cut off flow from D to F there, so we're going to count that 7. And so the capacity of that cut would be 8 plus 7, which is 15, right? Which looks like a relatively low cut for this graph. Remember that our aim is always to try to find the minimum possible cut. Okay, so we've got to still look and see if there's any other cuts we could make that would have a smaller capacity than 15. So let's kind of clear those and put all the water back flowing through the pipes in this network so everything's blue again. Now watch what happens here if we try another cut that goes through the edge from B to C. Now clearly that's cutting off flow from B to C. So once we make that cut, there's no more flow getting through that way. So that cut has to count. That 6 has to count towards the capacity of this cut. However, once we've stopped the flow from B to C, notice that we've also stopped the flow from C onto D and from C onto A. So all of these edges now don't have any water going through them once we've cut off that edge from B to C. And that's important because it means if we continue this cut up through the edge with a weight of 12, the edge from C to A, that cut doesn't actually count, or that edge, I should say, that edge doesn't count towards the cut capacity because the flow has already been stopped along that edge, okay? So that's a really key point. We don't have to count that 12 because the flow's already been cut off. Now, we haven't completely cut off the flow, so we still have to continue this cut so that it goes through sort of somewhere along the top to stop the flow of water getting to the finishing point or to the sink. But we don't have to count that 12 in the capacity of our cut. So if we continue through, I'm going to pick the smallest edge along the top there, cut off at the edge from A to E. Now, of course, that cut is stopping flow, so we do have to count that 8 towards our total capacity. But what you'll notice now is that the capacity of this cut is just 6 plus 8 because we didn't have to add the 12. And that cut capacity is 14, and that's smaller than the one that we'd found before. Okay, so this is like, as I said at the start, sort of what you might think of informally as like cutting this edge of 12 was like a backwards cut. We're actually going through an edge that already had its flow cut off, and therefore we didn't have to count it. And that's obviously really useful if you're trying to find the minimum cut, because sometimes these are like good sneaky exam questions where the minimum cut might involve having to go over an edge where you don't actually have to count the capacity of that edge because the flow has already been cut off in a previous section. So that's really one to watch out for. And I hope that kind of looking at it, thinking about water flowing through pipes and looking at these sort of colors along the edge might help. Obviously, you're not going to do that every time you do one of these questions, but while you're learning about it, it can be a good way to visualize it. So to finish the question off, if we were trying to find the maximum flow, well, we know the maximum flow is equal to the minimum cut. And in this case, the minimum cut capacity was 14.